Hello everyone. So welcome to lecture 14 on numerical analysis. So we are dealing with the solution of system of linear equations, the simultaneous linear algebraic equations. So we are seeing the iterative methods. So we have seen how to solve the system of linear equations by Jacobi iteration method, and we have also solved one example. Okay. So we have solved an example by Jacobi iteration method, and we have seen what is the difference between Jacobi iteration method as well as the Gauss-Seidel method. Okay, in the Gauss-Seidel method, the same system of linear equation is solvable if it is diagonally dominant. So then we take expression for x, y, z, and it is up to this it is same as Jacobi. Okay, then in the Gauss-Seidel method, after calculating the x1, that is first iteration of x, we are using the same x1 in the y1. After getting x1 and y1, we are using them in the z1. Okay, this is the only significant difference in the Gauss-Seidel and Jacobi iteration method. So before solving this equation, we have seen what is the difference between Jacobi iteration and Gauss-Seidel. So in the Jacobi iteration, so to calculate x1, y1, z1, we are using the initial value x0, y0 and z0 throughout this calculating three unknowns. Okay. Whereas in the Gauss-Seidel, we are calculating after calculating xn, we are using immediately in the y1. After calculating xn and y1, we are immediately using them in the z1. So this is the only difference we have seen between Jacobi iteration as well as Gauss-Seidel method. So now let us continue with the example. Solve the following system by Gauss-Seidel method. The same system we are going to solve now by the Gauss-Seidel method. Okay, what is the system given? 10x minus 5y minus 2z equal to 0, 3, 4x minus 10y plus 3z equal to minus 3. Okay, and x plus 6y plus 10z equal to minus 3. Okay, so now we shall see how to solve this by the Jacobi no Gauss-Seidel method. So what are the initial values? Initially we are going to take x, y, z. So let us see the solution. Yeah, so here I am starting the solution after knowing the difference between Jacobi and Gauss-Seidel method. Okay, solution. Right. So again, so here initial values are. So here in the Jacobi we used to take initial value for x also. Here initial value for x is not needed. Okay, and only y and z are needed. Okay, so now the x1 is equal to 1 by 10 into, so that means up to this we can take here. See in the previous example, yeah, so we have this system, the same system we are going to solve by Gauss-Seidel now. So up to this we can take as it is. Up to this we can take as it is. Right? Yeah. So now up to this we can take as it is. Once again I will write for the xyz expressions. Okay, instead of directly going for the x1, so we shall write xyz. Right. So what is the expression for x? So expression for x is x is equal to 1 by 10 into so 1 by 10 into 3 plus 5y plus 2z. Okay, and expression for y, what is a y value? From the second linear equation we take expression for y, so that is y is equal to 1 by 10 3 plus 4x plus 3z. So z is 1 by 10 into minus 3 minus x minus 6y. Okay, yeah. So now, so this we treated as equation 1, this as 2 and this as 3, right. So now we have initial value y0 and z0. So now using a Gauss-Seidel method, so by Gauss-Seidel method, okay, so we are going to solve this by Gauss-Seidel method. So now, so to calculate x1 we are going to use y0 and x0. Okay, so 1 by 10 into 3 plus 0 plus 0, because y is 0 and z is 0, therefore this is going to be 0.3. Okay, so now while finding y1 is what? 1 by 10 into 3 plus 4 x1. So instead of x0 we are going to use x1, that is 4 into 0.3 plus 3. Z is 0 because we have not got a latest root, so this is going to be 0.42. So z1 is 1 by 10 minus 3 minus x is x1 is 0.3 minus 6 into 0.42, that is y. So this gives minus 0.582, right. So this is the first iteration. So once you set in the calculator expression for x, expression for y and expression for z, we can use the answer key and simultaneously we can solve. So now we shall see for the second iteration, okay, x2, the second iteration. This is the first iteration, this is second iteration. So we solve for x2. So x2 is equal to what? 1 by 10 into 3 plus, earlier y0 and z0 are 0. So now they have been changed. Okay. So therefore it is 3 plus 5 into 0.42 plus 2 into minus 0.582. Okay. So this is going to be 0.3936. See, x has been improved from 0.3 to 0.3936. Okay, so similarly the second iteration for y, so that is 1 by 10 into 3 plus, see here 0.3 is used, x1 is used, instead of x1 we are going to use x2 now, so that is 4 into 0.3936 plus 3 into, so we are going to use z1 as it is, okay, 0.582. So this gives 0.28284. So similarly, the third unknown, that is Z2, second iteration of Z2 gives us 1 by 10 into minus 3 minus 0.3936 minus 6 into 0.28284. So this gives minus 0.509064. Okay. So you can see the improvised values of x, y, z in the second iteration. So now let us go for the third iteration. Okay. So in the third iteration, so again we are going to calculate for x3. x3 is same thing. Okay. So in this one equation 1, put the values of y2 and z2, you get a x3. Okay. So that is third iteration, 1 by 10 into 3 plus 5 into 0.28284 plus 2 into minus 0.509064. So this gives you 0.3396072. Okay. So next go for y3. y3 is again in the second equation. Use x3 and z2. Okay, use x3 and z2 in the second equation. We get y3 as 1 by 10 into 3 plus 4 into 0.3396072 plus 3 into minus 0.509064. Okay, so this is going to be 0.28312368, right? So similarly we get z3. So in the equation 3 use x3 and y3, so we get z3. So that is minus 3 minus 0.339672 minus 6 into 0.28312368. Okay, in the z3 use x3 and y3, we get a z3. So that is minus 0.503834. Okay, so now let us see, let us compare x2 and x3. x2 you can see 3.9, whereas this is 0.339. So there is a still this is a large difference. So whereas see y2, it is 0.282 and this is 0.283. Okay, this is approximately we have already arrived. Now let us concentrate on Z2. Z2 is minus 0.509, whereas it is 0.503. So still the convergence is required. So let us go for the one more step. Then I think we may arrive at the required convergence. Okay. Yeah. So now the fourth iteration. So there you calculate x4 using y3 and z3. So it is going to be 0.340794. Okay. So to calculate y3 use x3 and z2. Remember, to calculate y3 use x3 and z2, because z3 is yet to be found. So this is going to be 0.2851674 and z3. So to find z3 use x3 and y3, we get 0.50517. Okay, so now compare the x3 and x4. So this can be approximated to 2 decimals as 0.34. Okay, so now because it is 0.339, we can increase this one and make 0, this 0.34. Now see that both x3 and x4 are same. Okay, yeah. So now let us concentrate on y3 y4. So this is y4, sorry, fourth iteration, and this is also z4, the fourth iteration. Yeah. So here also 0.283, this can be also taken as 0.28, corrected to two decimal places. Okay, so therefore this is also almost converged. And compare z3 and z4. z3 is minus 0.503 and this is minus 0.50. Okay, so this is also converged up to two decimal places. So we can conclude up to two decimal places if required. Then up to two decimal places, the correct values, the values corrected to two decimal places are, what is the x value, 0.34, and what is the y value, 0.285, 28. Okay, up to two decimal places only, you can take 0.28. And what is the z value, minus 0.50. Okay, right. Yeah. So that means we have obtained the three unknowns x, y, z using Gauss-Seidel method. Okay. See, now we can compare this solution. This is solution for a Gauss-Seidel, for Gauss-Seidel. Okay. And you can compare the solution for a Jacobi iteration. See, x, what were the approximate value, 0.33, 0.28 minus 0.51. Okay, we have approximated that. So here also we got yes, almost same values, 0.34, 0.28 minus 0.50. Okay, right. So only difference we need to observe between the Gauss-Seidel and Jacobi iteration is that while using x1, the same thing. Okay, the x1 step is same in both Jacobi as well as in the Gauss-Seidel. But while finding y1 in the Jacobi, we are still using the initial value x0 and z0. Whereas while finding y1 in the Gauss-Seidel, we are using the latest root x1 instead of x0. So you can find a significant difference here. So but z0 is same. But while finding z1 in the Jacobi, we are still using the initial values x0, y0 and z0, whereas in the Gauss-Seidel, we are using the latest root x1 and y1 in the finding z1. Okay, so if this difference is understood, then both the methods can be used for finding the system of linear equations in a single uh, question. Okay, so next we shall see that the single question now. So we shall take one more example and we shall okay, so now one more question. Solve the system by Jacobi and Gauss-Seidel method. So we shall see the same system with the two methods and we shall compare which method is faster and which is slower. Okay, solve the system by Gauss-Seidel method, and this is an example thing. Example 3. Right. So the given system is 8x minus 3y plus 2z, okay, is equal to 20. 4x plus 11y minus z equal to 33. 6x plus 3y plus 12z equal to 35. Okay, so this system must have a by Jacobi as well as Gauss-Seidel method. So please try this one and we shall continue in the next class. Thank you.